Hello, you're welcome back. All right, so we are looking at another topic. All right, so we are going to be discussing capacitor in this particular video. All right, now, generally, a capacitor, right, is a device that is used in storing electric charge. So, so a capacitor is actually a reservoir of charges, electric charges. Now, how is a capacitor constructed? A capacitor, as you can see from this diagram, is made up of two parallel plates. All right, one is the positive plate, the other is the negative plate. Now, in between the parallel plate lies an insulator, all right, known as the dielectric, which um which actually produce a medium known as the dielectric medium, dielectric. So this dielectric medium is an insulator because it can be oil, paper, or it can even be just empty, just air in between. All right, it can be air in between the two parallel plates. So that is a dielectric medium. Okay, so now how does a capacitor operate? Now this is the simple electrical symbol of a capacitor. This is electrical symbol of a capacitor. Okay, so which of course represent two parallel plates. The symbol, okay, we have two parallel plates with terminal. These are terminal. So now one positive terminal of the capacitor is connected to the positive terminal of the battery or cell, while the negative is connected to the, of course, to the negative of terminal of a cell. So the reason for this is this: once this connection is established, current flows through the capacitor. So as current flows through the capacitor, what happens is stores electric charge. As I say, as I said before, a capacitor is a reservoir of electric charges. Okay, so now the quantity of charge, okay, let me use small letter q since that's what we are familiar with. The quantity of charge, small letter q, stored by a capacitor is directly proportional to the voltage or potential difference that is supplied across it. The higher the potential difference, the more charge it stores. Okay, so that way you know very well in mathematics. If I should remove the sign of proportionality and actually introduce a constant, all right, the constant I'm going to introduce is C. All right, so this C is what we refer to as the capacitance, capacitance of the capacitor, capacitance of the capacitor. All right, so which of course is measured in microfarad. So how do we define capacitance? Capacitance of a capacitor is simply from this expression. It's going to be the quantity of charge a capacitor stores per unit voltage that is supplied to it. Q all over V, the quantity of charge the capacitor can store per unit voltage that's connected to it. And of course, the SI unit is actually measured in farad. All right, in a small, abbreviated as F. So there are smaller units because of course um, we have the picofarad. Once you see the prefix picofarad, that simply means that we're looking at 10 raised power minus 12 farad. All right, we have the nanofarad NF, that is 10 raised to the power of minus 9 farad. Then we have the microfarad mu F. This is 10 raised to the power of minus 6 farad. Okay, then we have the milli, so on and so forth. So please take note of that. So capacitance. So anytime a capacitor is being constructed, okay, depending on what you want the capacitor to do, all right, you need to actually look at you have to measure the capacitance. All right, when you want to go to the electrical workshop to get the capacitor, all right, basically you need to specify the capacitance of the capacitor depending on what you want to use the capacitor to do. So now the question is, in constructing capacitor, how do we get to know the capacitance of the capacitor? That is what we are going to find out now. So we are going to derive another expression. Okay, so first of all, as we already know, the capacitor is made up of two parallel plates. Okay, two parallel plates. Okay, so in between the two parallel plates, we have the insulator, but that is not my major interest now. This parallel plate have surface area, okay, A, or cross-sectional area. Let me just area. All right. So now there's a distance. Let the distance between, okay, between the two plates, that is distance apart. D, let it be distance between the two plates. Okay. So we want to derive the expression, okay, for the measurement of capacitance. All right, with respect to area, and of course distance between the two parallel plates of the capacitor. Let's start. All right, we already know that electric potential is equal to electric field, then multiply by the distance. So the electric potential of this capacitor across this capacitor is going to be equal to the electric field that is set up in the capacitor multiplied by the distance between the two parallel plates. All right. So from here now, we can actually do some substitution. Electric field we also know is equal to electric flux density, okay, or better still, we know, okay, that electric flux density is equal to permittivity then times the electric field. So putting that into this expression, okay, all right, or but before I put it into the expression, flux density, okay, also we know that is given as flux all over area, right? And of course this is equal to, still gonna be equal to permittivity of that medium multiplied by electric field intensity. All right, okay, now flux we said is equal to charge, because of course the SI unit is coulomb per meter square, so flux is also equal to charge. So invariably flux, all right, of a conductor is equal to the charge of that conductor divided by area. So this is equal to epsilon 0 multiplied by E. So what is the whole idea is to make E the subject of formula. So of course I'm using small letter q. Let me not forget. Okay, so all right, so making E the subject, I'm going to have Q all over A epsilon 0, that is the permittivity of the medium. Now, if the medium we are looking at is just, in this case, is just air, okay? So what we are looking at is going to be epsilon 0, permittivity of free space, okay? So because air has relative permittivity of 1, okay? Which, of course, if you multiply it by the permittivity of free space, 1 times the permittivity of free space will still give me permittivity of free space. Okay, we are going to talk about that. So since if we are looking at air, all right, that is nothing is in between the two parallel plates, it's just air, then we are going to be using permittivity of free space. Okay, now let's now fit in everything into the original formula so that it will help us look at what, okay, get what we want. Okay, so invariably I have V is equal to the electric field, which of course is Q all over A epsilon 0, then of course multiplied by D. So if I rearrange this equation, Okay, if I arrange this equation, of course, I can cross multiply. All right, but if I arrange this equation, I'm very sure that if you do it to make Q all over V the subject, I will end up having A epsilon 0 divided by D. Okay, so just do that. That's what you're going to end up having. Rearrange this equation and make Q all over V the subject. You have A epsilon 0 divided by D. So invariably, we know that of course, Q all over V is the capacitance of the capacitor. So that means the capacitance of a capacitor is measured by, okay, multiply the area, all right, of the plate, then times epsilon 0, the permittivity of free space, since we are dealing with air. In this case, we are dealing with air, then divided by the distance between the two plates. Okay. But if we are dealing with another medium, okay, so another medium, don't forget, other mediums have relative permittivity. We've talked about that. Okay, so in that case, what you're going to have is A multiplied by the permittivity of the medium is always giving us the relative permittivity multiplied by the absolute permittivity. Don't forget, permittivity of other medium that is other than air, you must have to multiply by the relative permittivity of the medium, then times the constant absolute permittivity. So this is for other medium. Okay, so please take note of that. So that is how we measure the capacitance of a capacitor. Let's look at a typical example. Okay, let's look at a situation where you're being asked to calculate the capacitance of a capacitor of square plates whose length is just let's say 2 cm. All right, and okay, 2 cm. Okay, let me say length is 20 cm. Let me use 20 cm. Okay, then given that the relative permittivity of the medium that is used is 50. Simple. So we are looking at another medium having this relative permittivity. So the second formula holds. Capacitance of a capacitor is the area multiplied by relative permittivity times the absolute permittivity, or the permittivity of free space, then divided by the distance apart. Okay, let's say the distance between the two plates is 4 cm. Okay, so in this case, the area of a square is length square, L square. Okay, so converting this to meter, that's going to be 0.2 square, then multiply by relative permittivity, which is 50, then times absolute permittivity, which of course we know that is 8.85 times 10 raised to the power minus 12, if you can still remember. Okay, let me bring that down here. It's a constant. Okay, all right, let's go again. 0.2 square times 50 times the constant 8.85 times 10 raised to the power minus 12, then divided by the distance, which is 0.04. Let's work on this. So here we go. So I have 0.2 square, of course that's 0.04 times 50, then times 8.85. Okay, then divided by 0.04, 442.5. This is 442.5 times 10 raised to the power of minus 12. So in the standard form, I move this 1, 2, 3. So that I have to add 3 to the power of 10. So that's going to be 4.425. Then I move this 1, 2, okay, 2 times. That's going to be 10 raised to the power of minus 10. And that is going to be in farad. I hope that is well understood. is really very important. Okay, now this is just the how to calculate the capacitance of a capacitor with two parallel plates. What of the one that has multiple plates? Okay, multiple plates. Okay, with the same medium and of course the same distance. Basically, they use this for variable. They use this for variable capacitor, in which the area of the plate is being varied to change the capacitance. Okay, variable capacitor is. So what we are looking at is a situation where you have different, okay, evenly spaced uh, capacitors, evenly spaced capacitors. All right. So let's have how many plates? Let's say evenly spaced. So that's simply that I'm going to take out. So between between each plate. Okay, please pardon me if it's not, but just take note this is evenly spaced. So it's connected in such a way the terminal is taken out. All right. So the same medium, having the same medium. So this will form one capacitor. This will form another capacitor. This will form another capacitor, and this will form another capacitor. They are evenly spaced. Okay. So invariably, I have 1, 2, 3, 4, 5. 5 plates will give me 1, 2, 1 capacitor, 2 capacitor, 3 capacitor, 4 capacitor. So 5 plates gives 4 capacitor. So invariably 6 plates, okay, will give 5 capacitor. So for such capacitor, to calculate the capacitance, we use the formula n minus 1, then multiply by the capacitance of a single capacitor, which we know is giving us A, the area, epsilon, all right, relative permittivity multiplied by absolute permittivity, then divided by D. Okay, so anytime you have multiple plates. Okay, for example, let's say the capacitor that we've calculated the capacitance, this, all right, okay, is now is constructed into a multiple plate capacitor. This is the capacitance. So let's say like 5. Let's say what we have, the number of plates for this is 5 plates. So the question is, how do we now calculate the total capacitance? Simple. So in that case, that's gonna be, since there are 5 plates, that's 5 minus 1, then multiply by the capacitance that we've already calculated. So that's 4.425. 4.425 times 10 raised to the power of minus 10. So which of course is 4 times 4.425 times 10 raised to the power of minus 10 farad. So please take note of that. Okay, please take note of that. All right. Okay, I think basically that is it for this video. In the next video, we're going to look at different way capacitors can be connected, either in series or in parallel. So we're going to do that in the next video. Okay, so let's see in the next video. Thank you very much.